Imagine someone tasked you with building a state-of-the-art supersonic jet, right? But they forced you to use an engine blueprint drawn up in 1945.
Yeah, you'd probably argue that it's, well, physically impossible, or at the very least, just incredibly inefficient.
Exactly. But the crazy part is that is exactly what happens every single time you pull out your smartphone or, render a 4K video or query some massive cloud database.
It really is one of the most enduring paradoxes in modern engineering. I mean, we are looking at devices that operate at scales approaching the atomic level, yet they are entirely constrained by a conceptual bottleneck that is 80 years old.
Right. So welcome to today's deep dive. We're stripping away the user interfaces today and looking directly at the bare metal. Our source material is this really comprehensive manager's guide to information systems and computer devices.
Which is a fantastic resource, honestly. It maps out everything from raw silicon architecture all the way up to global network topologies.
Yeah, and just looking through these sources, the sheer physical evolution of computing hardware is, it's staggering. We've moved from the first generation of those room-sized vacuum tube arrays in the 1940s.
Right, the ones that used immense amounts of power.
Yeah, massive power sinks through transistors into integrated circuits, and now we basically live in the era of very large-scale integrated circuits, VLSI.
Which means we are packing billions of transistors onto a sliver of silicon the size of a fingernail.
But the architecture dictating how those billions of transistors actually talk to each other, that hasn't fundamentally changed. It's the von Neumann architecture.
Right, proposed by the mathematician John von Neumann in 1945. He established what we call the stored program concept.
Which, just to clarify for everyone, rigidly divides a system into 4 distinct activities. You've got input, processing, storage, and output.
And, that sounds perfectly logical on paper.
It does. It makes total sense. But as we'll see today, physically separating the processing from the storage creates a massive logistical nightmare when your processor is operating like billions of times a second.
Oh, absolutely.
So let's start right at the center of that problem, with the processing itself.
The central processing unit, the brain. To really understand how it operates, the source breaks the CPU down into 3 core elements. You have the control unit, the arithmetic and logic unit, the ALU, and the registers.
Right, and rather than just reading textbook definitions here, think of the CPU as, well, like a high-end commercial kitchen. The control unit is the head chef at the pass.
I like that analogy.
Yeah, because they aren't actually cooking the food, right? They were pulling the order tickets, which in this case are the sequential program instructions. They're decoding what needs to happen, and then they're just shouting commands to the rest of the kitchen.
Which leaves the actual heavy lifting to the arithmetic and logic unit. The ALU is basically your line cook.
The one getting their hands dirty.
Exactly. So if a command requires pure math, like adding, subtracting, multiplying, the ALU executes it. But it also handles logical operations, which are essentially gating mechanisms.
Like decision-making.
Right. The head chef asks, is variable A strictly greater than variable B? The ALU runs that comparison and returns a true or false. And that answer dictates the next branch of instructions the head chef issues.
And finally, you have the registers. So if the ALU is the line cook, the registers are, they're the cutting board directly in front of them.
The immediate workspace.
Yeah, it's that tiny temporary physical space on the processor die where they store the exact bits of data they're manipulating on this specific clock cycle.
What's fascinating here is that this physical proximity is absolutely vital. But, the metric everyone actually focuses on as consumers is just how fast that kitchen operates.
Right, the marketing numbers.
Yeah, you look at a spec sheet, and the primary number is always the clock frequency. We've gone from kilohertz to megahertz, and now we routinely see consumer chips hitting 5.1 gigahertz and beyond.
Okay, let's unpack this because, I see 5 gigahertz marketed everywhere, but if I try to run a complex 3D render or compile a massive code base, my 5 gigahertz laptop still stutters and hangs. So clock speed clearly isn't the whole story. Like, what is the clock actually waiting for?
Well, it's waiting for the instructions themselves, which vary wildly in complexity. This is why clock frequency alone is such a deceptive metric. A 5 gigahertz processor ticks 5 billion times a second, sure. But if a single instruction takes, say, 20 clock cycles to complete,
then that speed is suddenly massively diluted.
Exactly. This is why the sources emphasize IMALS and BIPS, millions or billions of instructions per second.
Oh, I get it. It's about how many order tickets the kitchen actually clears, not just how fast the chef can yell.
Precisely. And that throughput is heavily dictated by something called word length. Basically, word length is the sheer volume of bits a CPU can ingest and process in a single cycle.
So a 64-bit machine processes double the data per cycle of an old 32-bit machine.
Right. And today, we even have 256-bit processors.
Yeah.
You're essentially widening the pipeline. But even with a super wide pipeline, you run into the architectural philosophy of the instructions themselves. Specifically, RISC versus CISC.
Which stands for Reduced Instruction Set Computers versus Complex Instruction Set Computers.
Right. So in a CISC architecture, you have these really complex multi-step instructions weight directly into the hardware. Going back to your kitchen analogy, the head chef hands the line cook a recipe that just says, bake a cake, and the line cook spends like 15 clock cycles figuring it out and doing it.
Whereas RISC takes the exact opposite approach.
Yeah, RISC breaks it down into raw elemental steps.
Stir egg, pour flour,
Yeah.
stir.
Exactly. And because those RISC instructions are so incredibly simple, they can often be executed in a single clock cycle. But more importantly, it allows for deep pipelining.
Pipelining.
Yeah, so while the ALU is executing one instruction, the control unit is already decoding the next one and fetching a third from memory, all simultaneously.
That's incredibly efficient.
It is. And it's why the sources note that running specialized benchmark programs is really the only mathematically sound way to test a computer's actual throughput, rather than just looking at clock speed.
But there's a glaring bottleneck here, isn't there? Because a 5 gigahertz processor with a 256-bit word length and perfect instruction pipelining is still entirely useless if it takes an eternity to go find the next instruction.
Right, the chef and the cook are just standing around doing nothing.
Which is the fundamental flaw of the 1945 von Neumann design. The processor and the memory are physically separate, and that forces us into the extreme compromises of the memory hierarchy.
The storage hierarchy really is a constant battle against the laws of physics and, well, economics. You want memory that is instantly accessible to the CPU, holds massive amounts of data, and doesn't bankrupt the manufacturer.
But you can't have all three.
No, you absolutely can't.
The basic divide the sources highlight is between volatile and non-volatile storage. Volatile memory forgets everything when the power drops, while non-volatile storage like magnetic platters or optical disks with physically burned microscopic pits retains data permanently.
Right, your hard drives.
Yeah. But looking at volatile working memory, the modern architecture is wildly complex. I mean, we have L1 cache, L2 cache, L3 cache, and then main system RAM.
Okay, let's unpack this. If cache is the fastest, why not just build a 2 terabyte L1 cache and eliminate the memory bottleneck entirely?
Because of how that memory is physically constructed at the transistor level. Let's look at main system RAM first, specifically DRAM, or dynamic RAM.
Okay.
DRAM stores a bit of data using a microscopic capacitor. But the thing about capacitors is they leak charge constantly.
They just bleed power.
Exactly. So to prevent the ones from turning into zeros as they lose power, the system has to send an electrical pulse to refresh that capacitor thousands of times a second.
Oh, wow. Which I imagine introduces massive latency, right? Because the processor has to wait while the memory refreshes itself. Spot on. Now, compare that to SRAM, static RAM, which is what cache memory is actually made of. SRAM doesn't use those leaky capacitors. It uses a complex arrangement of transistors, usually a 6-transistor flip-flop, to hold a single bit of data.
So it never needs refreshing.
Never. It is blisteringly fast. But because it requires 6 transistors per bit instead of 1 capacitor, it is physically huge and exponentially more expensive to manufacture.
Okay, so you literally cannot fit a terabyte of SRAM onto a silicon die without making a processor the size of, like, a dinner plate?
Right, which would then introduce latency just from the physical distance the electrical signals have to travel. I mean, at those speeds, the speed of light becomes your enemy.
That is wild.
That's why L1 cache is microscopic, usually just a few kilobytes.
Yeah.
But it's embedded directly onto the CPU die itself.
Yeah.
It operates at the exact speed of the processor.
And when the CPU needs data that isn't in the L1 cache, what they call a cache miss, it checks L2, which is slightly larger, but sits just off the core, often on its own high-speed backside bus, so it doesn't fight with general system traffic.
Correct. And if it misses there, it checks L3, and finally it has to slog all the way out to main system RAM.
And even main RAM is constantly evolving to widen that bottleneck, right? Like, the industry moved from asynchronous DRAM to SDRAM, synchronous DRAM, which ties the memory operations directly to the system clock. And now we are on DDR5.
Right. And it's worth clarifying something that the sources sort of gloss over. DDR5 isn't just about packing more gigabytes onto a stick of RAM.
No.
No, it fundamentally overhauls the channel architecture. It breaks the memory module into two independent 32-bit addressable channels, which effectively doubles the data rate bandwidth compared to DDR4.
Ah, so it allows the CPU to pull data in parallel rather than waiting in a single file
Right.
line.
Exactly. It's all about feeding that central processor. But eventually, you need to store data permanently in massive volumes on non-volatile secondary storage. And when data accessibility is critical, say, for an enterprise file server, a single drive just isn't going to cut it.
Which brings up RAID, redundant array of independent disks. You take multiple physical hard drives and abstract them, so the operating system just sees one giant logical volume. And the sources detail several levels of this, but the architectural differences between them are actually fascinating.
Yeah, take RAID 0, or disk striping.
Yeah.
You split a file into blocks and write those blocks simultaneously across multiple drives.
Which is incredibly fast for read and write speeds, but honestly mathematically terrifying. Like, if you have 4 drives in RAID 0 and one physical drive dies, you don't just lose 25% of your data. The entire array is destroyed because you only have fragments of files. Zero fault tolerance.
Yeah, which is why enterprise environments immediately pivot to RAID 1 or RAID 5. Now, RAID 1 is simple mirroring, just writing the exact same data to 2 drives. But RAID 5 is really the gold standard for balancing capacity and redundancy.
Because it uses distributed parity. Here's where it gets really interesting, because the math behind distributed parity is so elegant. RAID 5 doesn't just copy files like RAID 1. It uses XOR logic exclusive OR operations. So if you have a binary 1 on drive A and a binary 0 on drive B, the RAID controller calculates a parity bit and stores it on drive C.
So if drive A suddenly catches fire and dies, the system just looks at drive B and the parity bit on drive C and mathematically deduces what used to be on drive A.
It just reconstructs the missing data on the fly.
It's brilliant. You get the speed of striping, you only sacrifice the storage capacity of one drive for the parity data, and you can survive a total hardware failure.
And if you need even more security, RAID 6 calculates a second independent parity block, allowing 2 completely separate hard drives to die simultaneously while the system just keeps serving files without dropping a single packet.
So, if we take a step back, we now have a system with a processor calculating at phenomenal speeds, supported by a highly fault-tolerant layered storage hierarchy. But a machine sitting in a dark room doing math is useless if it cannot interact with the physical world.
It needs to cross the boundary, which is the third pillar of the von Neumann blueprint: input and output. And the sources go way beyond the standard keyboard and monitor here. We're looking at voice recognition, translating analog audio waves into digital signals. We have GPS modules calculating exact latitudinal and longitudinal coordinates based on microscopic timing differences in signals from satellites.
Or consider the physical manifestation of data with Braille readers, where the output isn't pixels on a screen, but data physically actuating electromechanical pins, pushing them up against a flat surface for a visually impaired user to read.
Yeah, the diversity of I/O is amazing. The sources also make a crucial distinction regarding smart cards. A standard prepaid hotel key or like a subway pass is usually just a memory chip card. It has non-programmable logic. It literally just holds a static string of data.
Right.
But a true smart card has an actual microscopic microprocessor embedded in the plastic. So it doesn't just hold data. It performs cryptographic hashing and manipulates data on the fly before it ever sends it to the card reader.
But standardizing how all of these wildly different I/O devices talk to the CPU was, frankly, one of the greatest engineering hurdles of the 1990s.
Oh man, anyone who built PCs back then knows the absolute nightmare of hardware interrupts.
Oh, definitely.
Before the plug-and-play specification was developed, adding a sound card or a modem meant manually configuring physical jumpers on the motherboard to assign an IRQ, an interrupt request line, and a direct memory access channel. And if your mouse and your sound card tried to use the same IRQ to interrupt the CPU, the entire system would just crash.
The plug-and-play specification fundamentally shifted that burden. The architecture was overhauled so that every device has a unique identification code hardwired into it. So when you plug it in, the operating system reads that ID, dynamically assigns the IRQs, allocates memory addresses, and loads the drivers without any physical user intervention.
And the physical embodiment of that shift was USB, the Universal Serial Bus. It replaced this chaotic nightmare of 25-pin parallel ports, 9-pin serial ports, and PS2 connectors with a single standardized interface.
If we connect this to the bigger picture, it didn't just make things convenient, it democratized computing hardware.
Right. It made it accessible.
And once we solved the problem of connecting peripherals to a single computer seamlessly, the immediate next step was connecting those computers to each other, which scales our discussion from a single von Neumann machine up to global networking and communication.
Building a digital society. And just like a physical society, the infrastructure dictates the efficiency. The sources outline network topologies, and the architectural differences basically dictate exactly how a network fails. You have the bus topology, which is a single backbone cable that every node taps into. You have the ring topology, where tokens of data travel in a continuous one-way loop.
But the two most dominant architectures in modern computing are the star and the hierarchical structures. In a star network, every single endpoint connects directly to one central hub. It's incredibly fast and very easy to manage.
But the blast radius of a failure is catastrophic, right? Like, if that central hub loses power or gets compromised, the entire network drops to zero immediately. No node can talk to any other node.
Which is exactly why enterprise networks and cloud infrastructures rely on the hierarchical or tree topology. You have a root server connected to tier 2 switches, which connect to tier 3 routers, and so on. It creates isolated fault domains.
So if a tier 3 router dies, that specific branch of the network goes dark, but the rest of the tree continues communicating perfectly.
Exactly. And the way data physically traverses those branches, whether over coaxial cables, fiber optic lines, pulsing light, or microwave transmission, falls into 3 communication modes. Simplex is a one-way street, like a radio tower broadcasting to your car. You receive, but you can't talk back. Half duplex is two-way communication, but over a shared channel, meaning only one side can transmit at a time, like a walkie-talkie.
And full duplex allows simultaneous transmission and reception, maximizing throughput, but obviously requiring significantly more complex hardware to prevent signal collisions. But there's a nuance in the data transmission section of the sources that initially seems completely counterintuitive. It's the difference between synchronous and asynchronous transmission. The sources point out that asynchronous transmission wraps every single character in a start bit and a stop bit. That sounds like a massive amount of overhead. Why would anyone deliberately inject 25% more data into a stream just to send a message, instead of using the highly efficient synchronous method?
It really comes down to predictability. Synchronous transmission is fantastic for a massive data trunk line. Both the sending and receiving computers share a synchronized clock rhythm. The sender blasts huge blocks of data, and the receiver just listens to the beat and catches it. But human beings don't operate on a synchronized clock rhythm.
No, we type randomly. We pause. We hold down a key while we think.
Precisely. If a computer is waiting for human input, it has no idea when the next packet of data is coming. It can't synchronize a clock to a human, so it uses asynchronous transmission.
Ah, I see.
The start bit acts as a physical wake-up call to the receiving hardware, saying, hey, a character is arriving right now, start your local clock. The data is read, and then the stop bit tells the hardware to go back to sleep. It sacrifices bandwidth efficiency to accommodate the chaotic nature of human interaction.
It's hardware explicitly adapting to human psychology, which perfectly frames the final segment of our deep dive. We've built the processor, we've solved the memory bottleneck, connected the peripherals, networked the systems. Let's look at the actual citizens of this digital society today.
The modern computing ecosystem. The sources map out a traditional hierarchy. At the absolute top, you have mainframes. And these aren't just big PCs. They are heavily specialized for immense I/O throughput, capable of handling millions of concurrent transactions for, say, global banking systems.
Right. And below that are mini computers, which is a funny historical term because they are still massive, used as mid-range servers. Then workstations, heavily utilizing that RASC architecture we discussed earlier for floating point calculations in engineering and 3D modeling. And finally, microcomputers are standard desktops and laptops.
But that rigid hierarchy is breaking down, mostly because the locus of processing power is constantly shifting.
Exactly. The source highlights a fascinating architectural paradox happening right now. On one hand, you have the rise of the network computer, often called a thin client. This is a terminal on a desk that has a screen, a keyboard, and an Ethernet port, but absolutely zero local storage and virtually no processing power. It relies entirely on a central mainframe or cloud server to execute every single instruction.
We are centralizing the power to make management and security easier.
But simultaneously, at the exact same time, we are aggressively decentralizing power out to the very edges of the network through smart devices.
This raises an important question. If we are centralizing our heavy workloads in the cloud, why are we putting gigabytes of autonomous computing power into a wristwatch or a shipping container?
Because bandwidth isn't infinite. These IoT or Internet of Things devices, smart sensors, industrial trackers, autonomous drones are generating terabytes of raw data. If every sensor streamed raw data to the central server, the hierarchical network would instantly collapse under the bandwidth load.
So we push the processing out to the edge. The smart device uses its own local processor to run machine learning algorithms on the raw data, filters out the noise, and only transmits the highly compressed, valuable insights back up the tree. We've distributed the von Neumann architecture into everything.
Which really brings us full circle. We started by looking at 1946 vacuum tubes and the rigid 1945 blueprint of input, processing, storage, and output. We explored how the CPU relies on pipelining to cheat time, how the memory hierarchy uses cache to bridge the physical distance between silicon components, and how network topologies isolate failure.
The von Neumann architecture has survived because engineers have spent 80 years building incredibly clever workarounds for its inherent bottlenecks.
But I want to leave you with a final thought to mull over. Moore's law, the observation that transistor counts double every 2 years, has driven this entire revolution. We've gone from 32-bit processors to 256-bit pipelines. We've shrunk the physical transistors down to mere nanometers. But we're now brushing up against the immutable laws of quantum physics.
Quantum tunneling. Yeah, when a transistor gate is only a few atoms thick, the electrons just phase right through it, whether the gate is open or closed.
Exactly. Physical space on silicon is finite. We are literally running out of atoms. When we can no longer shrink the hardware and the latency between a CPU and its memory cannot physically be reduced any further, the 1945 von Neumann blueprint will finally hit its absolute unbreakable limit.
Which is a profound realization.
It is. When that day comes, whether it's through quantum computing or neuromorphic chips that mimic the human brain by fusing processing and memory into a single unit, well, we won't just be buying faster hardware. We will have to completely rethink what a computer actually is.
The next generation of engineers won't just be refining the kitchen, they'll have to invent a completely new way to cook.
Well said. So, next time you pull out your phone, take a second to appreciate the engineering. It's not magic, it's an orchestration of microscopic logic gates, distributed parity, and perfectly timed voltage spikes, all working furiously to keep a 1945 concept alive in a 21st century world. Thank you for joining us on this deep dive. Keep questioning how things work, and we'll catch you next time.